The title of my talk is Thermal Pretreatment and Conductive Material Mediated Anaerobic Co-Digestion of Organic Fraction of Municipal Solid. So this is not completely dedicated to biochar. So here we are actually doing we are looking to recover more energy in terms of the biogas from MSW and sewage sludge, and we did some thermal pretreatment to enhance the process efficiency. We faced some challenges during that time, and we used conductive material including biochar and other carbon-based conductive material and metal. So this is the outline about this talk. So the first one is the municipal solid waste generation fact in India. So this picture, this picture I took from Gurgaon, Banwadi landfill. So this landfill contains 20 lakh ton. So how to say 2 million ton of dump waste, and the government, it comes under near the NCR Delhi, NCR region. So now government is looking to eradicate or to clean and reclaim this land. So they are doing the landfill mining. So at that time we did some study there. So these are some facts about the global municipal solid waste generation. So I am not going to read this. So this is the Indian scenario. So we produce 62 million tons per day of waste, 70% collected, 24% has been processed, and 31 million ton dumped in landfill sites. Now the thing is, we have a higher fraction of organic content in the municipal solid waste, which is around 55%, and less recoverable or recycled material. The reason is we have a good informal sector like keepers, which actually take out all the recycled material before it goes to the dumping site. So there is largely the organic fraction of the waste. We see further attention. Now another key challenge or the problematic waste we have, sludge. So in past 10 years, wastewater treatment infrastructure significantly improved. So I am audible up to there? Okay. So now we have total generation of 75,000 MLD of wastewater nationally, and we have almost 45 to 50% treatment capacity. So now the next challenge is how to deal with the sludge. So this is a scenario I presented here. So the tons dry sludge per day and in different states. So usually we consider that if we are treating 1 MLD of wastewater, we are generating around 1000 kg, or we can say 1 ton of dewatered sludge, which is having 80% moisture content and 20% solids. On dry basis, we can say 200 kg sludge we are generating per MLD of wastewater we are treating. Now this is the total sludge generation. So in this figure you can see the green bar showing the total sludge as per the installed capacity, and the blue bar showing the total sludge as per actual capacity. So most of the treatment plant, they are running under capacity, maybe still their construction, sewerage construction is going on, the sewerage line is connecting to the wastewater treatment system. So the generation as per installed capacity is 7,000, approximately 7,000 tons per day, and actual capacity is around 3,500. Now we will treat the complete wastewater, it will produce around 14,500 tons dry solids per day. Disposal. So in India right now we don't have any sludge disposal standards, and major fraction of sludge is landfilled, or we use some fraction for composting and just to filling the low-lying areas. So we have these challenges, these two problematic ways to deal with. Now the key issue in municipal solid waste management are composting. So low value of product, limited waste volume reduction, and buyers are limited for compost, mainly in the metro cities like Delhi, Chennai, Mumbai. So landfill, high building operational land cost, and leachate management is the key issue. Then there is groundwater pollution and other things. Then open burning, it causes air pollution. Incineration would be a good option, but require high capital cost, generate ash, discharge heavy metals and other products, and low calorific value. So Indian municipal solid waste having a calorific value around 400 to 700 kilocalorie per kg. So as per our newly municipal solid waste rules in 2016, so we could incinerate a biomass if it having a calorific value more than 1500 kilocalorie per kg. So it is economically and energetically is not feasible to incinerate the municipal solid waste. Now the next option is anaerobic digestion. So these are some advantages of anaerobic digestion which is very well known. I am not going to repeat all these. But there are some drawbacks of anaerobic digestion of organic fraction of municipal solid waste like high solids content, toxic compounds, heavy metals are there, larger particle size, slow biodegradation because there are lignocellulosic fraction, heterogeneous nature and high carbon to nitrogen. So there are a lot of carbohydrate but less protein. So these are some problems. Then co-digestion could be an alternative. Co-digestion with sludge. So we have already two problematic waste. When we are combining them, they have their own benefit. So they will make the nutrient balance, they improve the C/N ratio, provide a buffering capacity, stabilize the pH of the digester, and dilute the toxic compounds and others. So ultimately, what we will get with this increased methane yield, improved process stability, and better handling of two problematic waste. Now, another issue of digestion of OFMSW and sludge is, for OFMSW there is lignocellulosic fraction. So cellulose and hemicellulose is tightly bound with the lignin. So degradation is slow due to recalcitrant structure. Then in sludge we have EBS matrix which is difficult to degrade. So hydrolysis of this the sludge is a slow process or rate limiting, which ultimately affect the process efficiency. So what are the options? We could pre-treat. So pre-treat with thermal treatment like microwave or conventional heating. We can do chemical, alkaline or acidic. We can do mechanical like ultrasonication. We can do hybrid, combination of all these things or two. So these are our key objectives of this study. So improve the efficiency of anaerobic digestion by thermal pretreatment of mixed waste and using the conductive materials to mitigate recalcitrant toxicity as a part of the thermal pretreatment to enhance the AD process performance. These are some different studies under these objectives we conducted. I'm not going to repeat this. So we collected the feedstock from IIT Roorkee campus. We segregated and shredded. So Banafsha was my PhD student who worked on this study. And this is the shredded MSW. So 95 to 98% is food and yard waste and remaining 2 to 5% paper. And now we collected inoculum from a nearby wastewater treatment plant based on afro-anaerobic sludge blanket process. And we collected primary waste activated sludge and mixed sludge from a nearby conventional activated sludge process system. So these are the raw waste characterizations. So I just highlighted some point which I would like to focus here. So you can see the organic fraction of municipal solid waste having a TS concentration of 18%, almost 18%, and approximately 75% VS part concentration is there. So if compared with the mixed sludge, it is 4% and 2.3% TS and VS. Then if we look at TCAN, so TCAN fraction in municipal solid waste organic fraction is 12% and municipal sludge is 23%, as municipal the mixed sludge is rich in the proteinaceous substance. Then carbon to nitrogen ratio also reflecting this carbon and nitrogen content of the feedstock. So 35% approximate in the OFMSW and almost 14% in mixed. So in the first study we optimized the co-digestion conditions. So what we optimized, the effects of co-digestion, the best sludge combination, mixing ratio and total solid percentage. So this is what we did: sample collection, Then we did raw waste characterization, pH, alkalinity, TS, VS and other parameters. Then we did BMP assay. So in the first test we did the best mixing ratio. So among these 50-50, 70-30 and 80-20, 90-10. So MSW and sludge. So we observed that 80-20 ratio was the best and we achieved the highest biogas yield. Then we go ahead for the best to realize the best total solids percentage, and we tested 4 different total solids percentage. We realized that approximately 10% TS gives the best biogas yield over others. So we get best sludge combination with the solid waste, which was the mixed sludge. Best solid percentage was around 10%, and best mixing ratio was 80. Now the thermal chemical pretreatment. We did thermal chemical pretreatment and optimized some conditions: treatment temperature, reaction time, and applied dosage. So we pretreat the mixed waste, and we use the thermal pressure reactor. So we split this into the one is thermal only and the another was thermal with alkaline. So in thermal only we tested 5 different temperatures from 100 to 200 degrees Celsius and with 4 different reaction times of 30, 60, 90 and 120 minutes. Then we realized the best reaction time on the basis of the best solubilization we achieve on the basis of COD, protein and carbon. Then we did the BMP assay of the pretreated substrate and we get the highest biogas yield at 125 degrees Celsius. However, we achieve highest solubilization at 75 degrees Celsius. So for the second experiment we did thermal alkaline, the same 5 temperatures we took, and we used alkaline doses of NaOH 1357 gram per liter, and we realized the best alkaline dosage with the thermal with the different temperature was 3 gram per liter, where we achieve highest solubilization. And the BMP assay of the thermal alkaline pretreated substrate gave us that the best biogas yield was at 125 degrees Celsius and 3 gram per liter NaOH. So this was important. So above 150 degrees Celsius, we got a significant decrease in biogas yield, realizing the formation of recalcitrant HMF and furan derivatives. So despite getting a higher solubilization in terms of the soluble COD, we get less biogas yield above 150 degrees Celsius due to recalcitrant. Now, as you all are aware, that the formation of recalcitrant compounds largely based on the Maillard reaction, which is a complex reaction between the amino acids and reducing sugar. So we have protein there, contributed by sludge. We have carbohydrate there, contributed by the MSW. So this reaction under different stages leads to formation of intermediates like phosphorus, HMF and melanoids. So how to minimize the adverse impact of recalcitrant compound on anaerobic co-digestion, mainly at high temperature. So we used granular activated carbon and biochar, realizing that they have high adsorption capacity, they are having a higher surface area. So we pretreat the substrate at 3 different temperatures of 150 degrees Celsius, 175 and 200 degrees Celsius. Then we check the HMF and furfural concentration, which was significantly high, up to 150 milligram per liter for HMF and furfural also up to 100 milligram per liter. Then what we did, we add conductive materials in the pretreated feedstock. So we keep the concentration 25 gram per liter of both as per our earlier study we did, where we realized that about 25 gram per liter, either there was no significant improvement or it was almost negligible, maybe due to carbon toxicity or oxidative stress. We are not sure, we didn't go into that aspects. Then we did the BMP, we checked the biomethane potential of pretreated and we added conductive material. So I would like to clarify here, we added conductive material separate. We have not mixed the GAC and GBC. GAC in separate bags and GBC separate, just to compare the performance. So we observed that it reduced the inhibitory effects of recalcitrant and increased the biogas yield. Then these are the outcomes. So 44 to 51% recalcitrant removal we observed by GAC and GBC addition, and more than 45% higher biogas yield we achieved with GAC and GBC at 175 degrees Celsius temperature with 3 gram per liter. So these are some reasons. GAC and GBC, they have high efficient absorption capacity, large surface area, they support high microbial growth, they stimulate direct interspecies electron transfer among acid formers and methanogens. So there are 3 different reasons were assumed for this. Okay. Now we did another study in the next to this to realize what if we, rather than doing the downstream treatment, we remove the refractory materials or compounds or minimize their production at first place. So what we did, we used ferric metals and ferric salts, FeCl3, which is a strong oxidant, and it minimized the polymerization of intermediate products, which ultimately lead to the formation of Anaerobic. So these are our results. So different doses of FeCl3 or Fe, and we checked this with 3 different temperatures of 150, 175 and 200 degrees Celsius. So you can see I highlighted some part of this 5-HMF and perfurans, and you can see 0 means there was no addition of ferric salt, and at 10 milligram per liter Fe dosage, we observed a significant reduction in HMF and perfurans. So in all cases, we achieved 45 to 60% reduction in HMF and perfurans. So above this concentration, we didn't get too much variation or too much reduction. Maybe FeCl3 reacts with water, make oxides of ferrous, and then it reduces the pH. So we observed that 10 milligram per liter dose was the best to reduce the recalcitrant formation to the maximum. So these are the result of this study. We treated, we conducted this in under 2 stages. One with the control, where we doesn't add any ferric salt, and other with the addition of ferric ions. Then we realized that optimum dosing of Fe3 was 10 milligram per liter, and we achieved the best reduction in recalcitrant formation, that is up to 66%. We achieved highest biogas yield at 175 degrees Celsius with 3 gram per liter NaOH dosage, and we achieved 34% higher biogas yield over the control, non-Fe mitigated digester. Then, in the next stage of this study, we conducted semi-continuous. So, on the basis of the optimized results, we did a semi-continuous study. These are picture of the semi-continuous reactor of 6 liter capacity each. So, we operated one control condition without any pre-treatment. Then the thermal pre-treatment with 125 degrees Celsius and the thermal alkaline pre-treatment. So, we applied various organic loading rate, and respective HRTs was 30, 20, 15 and 10 days. So we operated for 160 days. For each HRT we run twice once we achieve steady state. So these are the results. So methane yield you can see here. So these green line showing for thermal alkali pre-treated digester. The blue one is the thermally pre-treated and red one is the control. So these results are combined for all the HRTs we studied. So this picture revealed the highest methane yield we achieved with 15 days HRT and 5.1 kg per meter cube per day for organic loading rate. Usually, if we are digesting the organic fraction of municipal solid waste, so large scale plant, usually they run at 25 to 30 days HRT. Then you can realize we just minimize it up to almost 50%. So we need smaller digesters, so capex will be less if we integrate a thermal pretreatment. Then we achieve 45% higher biogas in comparison of control and 10% higher than the thermal pretreatment. This is the VS removal. So pink dot showing the thermal alkaline pretreated, and the blue star, this is showing the thermally pretreated. So VS removal under different sets of conditions, we achieve 52% VS removal in thermal alkaline pretreated digesters, which was 57 and 11% higher than the control and thermally pretreated. So in this project, we scale up from 250 ml to 150 kg capacity. So our 150 kg digester also replicate the results of semi-continuous study. So I didn't present these results due to time constraint. So conclusion, I think I already repeat all my conclusions, so repeat again. And thank you very much.
Long live India and France friendship.